Welcome to another week of online organic chemistry. This week we're going to be discussing chemical kinetics with an emphasis on the SN1 reaction, which we covered last week. For our textbooks, it's section 20, pages 321 through 26. And let's go ahead and get started. If you remember from last week, we covered the SN1 reaction, that's unimolecular substitution nucleophilic reaction. We took tert-butyl alcohol in the presence of hydrochloric acid, and if you were in the lab, you would make tert-butyl chloride in water. So we're going to kind of look at this in terms of the kinetics of what's going on to determine why things are happening and the rate that they're happening in. And we need to go over a couple things. Talked a little bit about it last time, but this reaction is called a solvolysis. And anytime you see solvolysis, that basically means where you have a solvent, of course, because we're talking about solvolysis. But when your solvent acts as the actual reactant, that's a solvolysis reaction. And for this case, both the water is going to be the main thing. So we also have, it's a solvolysis reaction, but we also have a hydrolysis. So, and hydrolysis is just a type of solvolysis where water is included. You can also have things like alcoholysis where your alcohol is the solvent and that's the reactant as well. So there's a whole bunch of things, but it's just different types of solvolysis. So anytime you see that, that's just any type of reaction where your solvent, which generally is only used to allow things to be miscible together and stay in solution. In this case, solvolysis, the solvent actually acts as a reactant as well. We're going to go over the mechanism a little bit more in depth than we did last time, and we'll start seeing this a little bit more every lab from this point on. But in terms of the solvolysis reaction, this is also a nucleophilic substitution reaction, just like the reverse. And this time, since it's a solvolysis, and in this case a hydrolysis, water is actually going to act as the nucleophile. It's got the lone pairs on the oxygen, so that can easily act as a nucleophile when it comes to contact with any type of like carbocation or something like in this case, which it will. If you see on the mechanistic states at the top, your tert-butyl chloride, that chlorine is a very good leaving group, so it'll pop off over time slowly. And once it pops off, you form a tertiary carbocation, which is self-stabilizing, and a chloride ion in solution. And if you have water, that water can really quickly go back in on that positive charge on that central carbocation. Now, a lot of people might ask, well, yeah, that can do it, but the chloride is an anion. It's got just a true negative charge. Why doesn't that go back and react and form the tert-butyl chloride again? Well, the true answer is it does. It does all the time. Basically, any type of reaction, you've got a lot of side reactions going on. But what we're really only concerned with in this specific reaction is that water popping back on. You're always going to get equilibrium between, like for instance, this case, that top line, tert-butyl chloride, that chlorine popping off, and then you having the carbonium, the carbocation in solution, and that chlorine is going to pop back, water's going to pop back, a whole bunch of things can go in there. But when we're talking about specific reaction types, we're generally only concerned about one specific thing. So if you ever ask yourself and see these, well, why isn't this working? Generally it does. It does do stuff like that. But, use of different solvents and stuff like that, and you can focus on specific things you want, which is in this case solvolysis with water. So if you just completely inundate the solution, you have water in excess, it doesn't matter that you have a few chloride ions popping off, that water is going to pop onto the carbocation a lot more frequently than the smaller amount of chloride ions that might be in solution. So basically, like we said last time, that chlorine coming off is very slow. Because it's much, much, much slower than that water seeing that carbocation and bolting itself on. That's the chloride elimination step at the top there is the rate determining step because it is the slowest of the two steps that happen. And because that's the one step, it's the slowest because you see the water going to the carbocation is a fast step. And then the chloride basically pulling a hydrogen off of the water because it's a sterically hindered bulky material there at the end of the hydrocarbon. And the second line on the right, that's very fast too, because it's going to happen really quick. You're going to form strong acid that's favored. Also, getting rid of that hydrogen and forming a alcohol group is favored to reduce strain on the molecule. So that's a fast step as well. So your slow step is the very beginning, that chloride leaving group popping off. And because if you look at that, there's only one molecule in question. That's all that matters is the tert-butyl-chloride at top. And since that's the only thing that matters in the rate determining step, we can see that this is going to be an S-1 reaction, a unimolecular substitution reaction, just like the reaction we talked about last week. This is actually the same reaction, it's just we're looking at it backwards. So just like last time, this is an S-1 reaction as well. Talking a little bit more about this, it's an S-1, so only the rate of the reaction, how fast the reaction goes, only is going to be determined on the tert-butyl-chloride, because that's the slow step, is that chlorine popping off. Now, even though I talked about earlier, if you have a whole bunch of water as a solvent, that's going to pop on to the carbocation quicker than the chloride ion, just because there's so much of it. That's true. It does go on faster, but that is not what determines the rate of this reaction. What determines the rate of reaction is waiting around for that chlorine to pop off, because basically, kinetically, as soon as that chloride pops off of that tert-butyl-chloride, that water is going to come in instantly, just bang, just quicker than the eye can see. It's in femtoseconds, 10 to the negative 25th of a second. So it's really, really fast. So no matter how much water you have, it's not going to speed up. As long as you have just some water, it's going to be the same exact reaction. And since this is an S-1, what we're going to do with the reaction is the rate of the reaction for an S-1 is going to be a K, which is a rate constant, times the concentration of the one molecule in this case that matters, which is your tert-butyl-chloride. So kind of there near the bottom, you can see the rate reaction for this rate reaction equation for this specific S-1 reaction. And all S-1 reactions are going to look like the rate. They're going to look just like this. The rate is always going to be equal to some constant times the concentration value for your one unimolecular molecule in question. We can take that rate reaction equation from the previous slide, rate equals K times the concentration of your molecule, and we can do some derivation on it to actually get numbers and plug things in and figure out things over time, which that's kind of the purpose of all these rate reactions. You want to see if it's, if we wait 15 minutes, how much of a concentration are we going to have left, how fast is the reaction going to go, stuff like that, stuff you actually can use for research or extrapolation. So let's just say we have the tert-butyl-chloride concentration. We'll just see it's a bracket C, and at any specific time, that time concentration will be C underscore T, like on that first line. That's what we're going to call it. So what we can say for an S-1 reaction, which only determines on the concentration of C, your rate is equal to some constant K times the concentration of your, in this case, tert-butyl-chloride at time T. So basically what we can do, we can say that over time the rate of tert-butyl-chloride going away is equal to that constant K times the concentration at time T. And when we're talking about rates and things going away, that's just a derivative. So we can say the derivative, take the derivative of your concentration at a specific time, or dCt dt, that's going to be equal to your rate constant times the concentration at that time. And because, remember, you're losing your reactant, tert-butyl-chloride, you're losing some and it's becoming the tert-butyl alcohol over time. So you're going to have a negative sign in front of that rate. So it's a negative rate. You're losing some of your initial stuff. And that rate, since it's a unimolecular reaction, S-1, is going to be equal to a constant K times that initial concentration at a specific time. So we're going to label this thing kind of in the middle as that equation 1. So what we can do with this is now we can start, if we want to start using specific times to judge from like start to finish or start to a specific time, we have to get rid of those derivatives and basically kick out just an actual time as a variable. So when we start the reaction, we're going to set time equals to 0, and the concentration of your tert-butyl-chloride for this will be just arbitrarily will be the bracket C at 0. So we have to get rid of that derivative. So anytime you want to get rid of a derivative mathematically, you integrate it. And you really don't really need to know how to do this for this specific lab. If you were in the lab and doing it, you would use like an Excel or some type of system like that. But it's just a very simple thing. Anytime you're working with stuff like this, you want to get your variables on one side, your derivatives on the other, so you can kind of manipulate this. And what you end up with is you can end up with the derivative of a variable divided by that variable again. And anytime you see that, when you integrate that, that's always going to be the natural log of the variable over itself. So basically, don't need to worry about that too much. You're probably not ever going to see that again in this class. You won't have to do it by hand for anything. But just remember, anytime you see a first order as an SN1 rate constant, when you integrate it, you're always going to get a natural log for the first order for SN1s. Just remember that. So when you do integrate it and you move the variables around, you end up with the negative, because it's a loss, negative natural log of the concentration of your tert-butyl at a time divided by the concentration of tert-butyl at the initial, and that equals your rate constant times whatever your time is for the reaction. So you can just plug everything in, remembering that the natural log is the same thing as a base log times 2.303. So negative 2.303 log of C of t over C naught equals KT. And you can just come out to just really simple equation 2 there at the very bottom. And at that point, you can plug stuff in. You know your initial concentration, because that's what you put in the test tube or your beaker or whatever. You're going to know a time, or you can judge a time. You can say, what's going to happen at 10 seconds, 20 seconds, an hour, stuff like that. And so you're going to have, there's only going to be one variable left out. You're either going to know the starting and the finishing concentrations, so you can figure out how long it takes, or you're going to know the starting concentration always and how long the reaction you're going to let it go. So then you can figure out what the concentration is at that time. So anything you would need, you can figure out from the integrated rate law equation, which is equation 2 there. Some other little derivations and manipulations we can do is comparing different molecules in the reaction, because you might not be able to determine at specific points in the reaction how much of something you have, if it's an intermediate or something like that. But the thing to notice here is when you go backwards and do this hydrolysis SN1 reaction with tert-butyl chloride, you're generating acid, you're generating hydrochloric acid. And generation of acids or bases is always really easy to track, because you can do it by simple titrations, pH checks, stuff like that. So it's really easy to track. So what we can look at stoichiometrically with this reaction is, for every one molecule of tert-butyl chloride you start with, you end up balanced with one molecule of hydrochloric acid. So what we can do is we can take those initial and at a specific time concentrations of tert-butyl chloride and kind of rewrite them in a version of hydrochloric acid. So if we can get that and base everything on hydrochloric acid produced over time, we can actually use simple titration to track these reactions, instead of you having to do an NMR or track something like that, or a higher end setup using other instrumentation. We just really basic benchtop chemistry. So the thing to look at here is when the reaction begins, of course, you've got 0 hydrochloric acid. And when the reaction is fully complete, which we'll just call T equals infinity, all of that tert-butyl chloride will be gone, and it will be converted into hydrochloric acid. So we're going to use that, and you can just say the concentration of HCl at time infinity is equivalent to the concentration of your initial tert-butyl chloride, because it's 1-to-1 ratio. There's the same molar equivalents, so there should be concentration equivalents. So basically, just some simple manipulation and plugging that relationship back into that equation 2 from the previous section, we come up with equation 3 down at the bottom, which is the 2.303 times the log of your infinity concentration of HCl minus the time concentration of HCl divided by the infinity concentration of HCl. So now we've changed our rate reaction, instead of worrying about the tert-butyl chloride, which might be hard to track, to something we can track very easily in terms of the hydrochloric acid. As I mentioned in the previous slide, we can determine those values of HCl at a specific time by, at that time, just withdrawing a little bit of your a solution that's reacting with a pipette. You got to be very accurate measure when you measure it. And anytime you're withdrawing something from an ongoing reaction, this is called, when you take it out, it's called an aliquot. And so if you see that word aliquot, aliquot, that just means part of a reaction you're taking out while the reaction is still going. It's just something simple like that. And then what we're going to do is, because that's still reacting, you might still have some terbium chloride stuff in there. You're going to quench the reaction. And for this reaction, we know, you all probably don't know, but it's a known thing that you can quench this reaction with acetone. It'll completely stop the reaction from proceeding. So you would withdraw a small aliquot of your reaction, you would quench it with acetone, and then you can titrate that with a base, because we know we're working with acids in this case, so titrate it with a base. And when things get neutralized, you can figure out exactly how much of that acid is in there, because you'll know how much of the base, your molarity of the base, how much you're using. So it's just a really simple calculation to determine how much the acid's going to be, because you'll try to get things to react in a 1-to-1 ratio, like hydrochloric acid. So most likely you'll be using sodium hydroxide, because it's a simple 1-to-1 reaction here. So as long as you use the same base, you're good. As long as you know the exact concentration of that base, that's fine. It doesn't have to be exactly like a 1 mole or something like that. You can use a 0.25, whatever. As long as you know what you got, you're good. So basically, since we're going to use sodium hydroxide to titrate to figure out how much HCl we have in solution, we know HCl, and like I said, HCl and AOH react in a 1-to-1 ratio. So we can basically just take our values for our NaOH used in this titration and substitute them directly for that HCl values. So there at the bottom, that the equation 3 we did earlier, where we changed everything to HCl, you can just plug in the NaOH and back in there, and we're going to use the milliliters, because this is basically, when you're doing the log scales, it kills all units. So, we were talking about concentration of something, moles per liter, but now you notice we're just worried about milliliters. And we can do that because no matter how much of this NOH we use, it's the same concentration every single time. So mathematically, you can just take that out. It's considered a constant. You can just take it out of the whole thing and just divide it out by itself. It's pretty simple. So instead of having to worry about different concentrations of HCl versus NaOH and how long it's going to change and what's it going to take to neutralize, you can just get rid of all that, because your NaOH concentration is constant the entire time you're titrating. So you can just work with the value of your milliliters. And at that point, it's just a simple ratio. And you're going to take the log of it anyway, so any units that are in there are gone. So that's just a trick that over time you'll learn for dimensional analysis type stuff. So once you do that, you can transform the equation 3 to basically, at the very bottom, the log of your infinity value minus the at time value of milliliters of sodium hydroxide divided by the infinity value of sodium hydroxide. And that equals your rate constant divided by 2.303 times your time. So we've gone from your initial rate, which was just a broad setting based on terbium chloride, to changing that to the volume based on hydrogen chloride produced, and then changing that to milliliters of sodium hydroxide to get this equation 5. That's pretty much all the lead up you need for this specific reaction. So now we'll go into the actual laboratory procedures as if we were in the lab. So this is going to be a titration. So I'm sure y'all did it in Gen Chem 1. Hopefully y'all did. But it's just a simple setup. You get a ring stand with the clamp, and you get a titration burette, one of the long glass ones with the graduated marks on it, and the little stopper at the bottom to release the liquid. And you're going to take a stock solution of sodium hydroxide. For this lab, the TA would have produced 0.04 molar or normal solution of sodium hydroxide. And that's basically just because we know already the concentration of hydrogen chloride that's going to be produced, because this reaction has been done by us for so much. So this makes it a lot easier with your numbers and everything, just to help you out. So you would fill the burette there with 50 milliliters of this 0.04 molar sodium hydroxide solution. And then you would prepare the stock solution for your reaction. So you would measure out 1.2 milliliters of terbium chloride, and you put that in a volumetric flask. Now, if you've never used a volumetric flask, that's a little diagram of it down there on the bottom left. Volumetric flasks are incredibly precise. Anytime you want a precise reading or to make a stock or a standard, solution, you always use volumetric flasks. Because if you get a beaker or an Erlenmeyer, even though it says, there's a line on it that says it might be 250 milliliters, those things aren't nearly accurate. You can't use that as an accurate judgment. It's basically an eyeball napkin math. You could be 50, 25 or 50 milliliters off very easily. Volumetric flasks have a little mark on the neck, and it's basically less than 0.01% variance. If you fill it up to that mark like you're supposed to, it's basically going to be exactly what it's supposed to be. So a 100 milliliter volumetric flask, you fill it up to the mark, it will be 100 milliliters, or 99.9 or 100.001, that stuff like that. But it's going to be very close. So anytime you're doing stock solutions or standards, always use volumetric flasks for measurement. Makes it much easier. So once you got the 1.2 milliliters of terbium chloride in your volumetric flask, you're going to fill it up to the mark with another solution that would have been made. It's basically a water alcohol mixture, 1-to-1 ratio of deionized water and 2 propanol. So that's basically the stock solution that would have been prepared ahead of time. You would have mixed it in your own specific volumetric flask, and mix it well, and then let it set and everything happen nice and easy. And what you're going to do is, as soon as it's all mixed, you would take a stopwatch and you would start timing. And basically, you're going to time for this lab, in the actual lab, would be 75 minutes. And you don't stop your stopwatch. Just keep the whole thing going, and you're not done until that last 75 minutes is up. Okay. Now we need to get set up at specific times and also set up in what's called an infinity solution, or basically a solution that's left alone to fully react. So the first thing you would do in lab is prepare your infinity solution. So you would take 10 milliliters of that stock you made in the 100 milliliter flask, and you'd put it in an Erlenmeyer flask. You'd add 10 extra milliliters of water, so you have excess water so the hydrolysis reaction can go. Shake it up, mix it well, and then you're just going to set that aside for the entire lab. You're not going to worry about checking the rates of that because you just want that to be completely reacted to endpoint, and that's going to be your infinity solution. That's going to be the maximum amount of hydrochloric acid produced when that reaction is done, and you set that aside. Once that's set aside, just keep a watch on your stopwatch, and basically at 10 minutes, 20 minutes, 35, 50, and 75 minutes, you're going to take aliquots of your reaction, quench them, and check the titration to figure out the endpoints, stuff like that, record the volumes. And this is what you're going to use to determine the rate of the reaction. So once that stopwatch is 10 minutes, you're going to take a 10 milliliter aliquot out of your stock solution, and you're going to put that in a 125 milliliter Erlenmeyer flask. And this is where we're going to add the acetone to stop the reaction, because we want it to stop at that point and take up basically a freeze frame of the amount of hydrogen chloride produced. So you're going to add, at that point, once that's in there, and you swirl it up a little bit, add a couple drops of an indicator called bromothymol blue. And because we've got acid in there, it's going to look kind of yellowish. Bromothymol blue is yellowish. At neutral, it's blue. Acidic, it's yellow. And once it becomes basic, it starts turning kind of green. So it switches from blue to yellow to green, that range. So you're going to titrate with your burette full of sodium hydroxide, very slowly, drop by drop, stirring after every drop, making sure it's fully equalized and, settled and everything. And you just keep adding drops slowly until you see that very pale green, just the slightest bit of green that stays. And you might swirl it and set it down, it might go away. But just keep adding a tiny little drop at a time. And then once that pale green is there all the time, and not deep green, just pale green, that's going to be your endpoint. So you can look at your burette, and you can see how much sodium hydroxide in terms of milliliters has been used, and you're going to record that volumes for 10 minutes. And that's going to be the volume that you're going to plug into that, finalized equation 5 we used earlier. So you're going to do this at, like I said, at the 10-minute point. You're going to repeat the exact same process at 20, 35, 50, and 75. So you're going to have a total of 5 data points for specific times, and then you're going to have a data point for that initial, you got your initial at 0 time and your infinity, which is the solution we made earlier and set aside. All right, once you have all your values, your 5, and then once those are done, you can do the infinity. And you're going to take same process. You would take 10 milliliters out of the infinity solution. You would titrate that with your sodium hydroxide, recording the volume used when it turns green. And once you have all those values, those 6 values, you're going to take that equation 5 from the previous slide. You're just going to plug those values in there, because remember, each equation 5 required a milliliters of sodium hydroxide at infinity, which is that last one you do with the solution set aside, and milliliters of sodium hydroxide at a specific time. So it required those 2 values. So you're going to plug those in to your equation 5, calculate that number, and just plug it into a little chart that we're going to use to graph. Once you have your little chart, if you had your laptop in lab, you could put it directly into Excel or any other spreadsheet program you might have. So it's just a simple, in terms of charting it, axes at the very bottom is going to be your time, from time 0 to 75 being the longest that's needed. And then your y-axis is going to be equation 5, the value you get from that. So it's the log of the infinity milliliters minus the time milliliters of sodium hydroxide divided by the milliliters of sodium hydroxide at infinity again. And once you have those two values, you just plug them in, graph it using Excel or whatever spreadsheet you want. And you would also require a best fit linear solution equation for this. You can just click on the data points in Excel, right click it, and there's an option to generate the equation. And you can choose linear or polynomial for this, because it's going to be fairly linear. Linear works fine. To see how close of a fit it is, you can ask Excel to spit out its R-squared value, which is basically just a statistical method to determine how accurate to the fitting model it is. And what you're looking for is a value for R-squared really, really close to 1. Generally, you want at least 0.99. Once you get around there, you're good enough for government work, as they say. But if you're closer to 0 than you are 1, then it's not a very good fit, and you either might have messed up with the data, or a little bit too slow, or you went too fast on your titration and were a little bit off. But generally, this with stuff like this, is pretty easy to get your values. And you can tell, like, by looking at this example, looking at those 5 data points on there, it almost looks like a straight line anyway. So you can tell your R-squared value would be pretty close to there. So that's basically the lab. It would be 75 minutes plus another 10 or 15 minutes of setup and then clean up. It'd be a pretty quick lab for this week. You just graph everything in Excel and show this to your TA before you're able to leave. And this is just an example of how you can figure out or determine if your thoughts are correct on a type of reaction. If you think it's an SN1 reaction and you graph it, this is what you'll be looking for. If this all works out and everything works as intended, you'll be able to do this and then extrapolate. If you use different concentrations or different times, or you needed to know, if I let this reaction go for 15 minutes, how much of our reactant is going to be converted, stuff like that. So you can do this with every other type of reaction. And we'll be doing stuff like this when we talk about SN2s and elimination reactions. We'll also go over this stuff, because you start getting to bimolecular or third or fourth order reactions. So the math gets a little harder, more things to track. But this is just a really general gist of how kinetics can be measured in a lab, and you can take those kinetics and then extrapolate based on determining concentrations of your reactants or your products, how long things are going to take. And for this SN1 reaction, pretty simple. So I hope you at least learned something, and we'll be talking to you next week, and have a good weekend.